Welcome to ACE Teachers Online, a series of tutorials for students. My name is Ross, and today we'll be going through a HSC Chemistry question on the Haber process. Today we'll be forming a calculation related to the Haber process. In this particular question, a chemist is providing 700 litres of feedstock into a reaction vessel to produce ammonia. This feedstock has both nitrogen and hydrogen in the correct stoichiometric ratio in the feedstock, but is also contaminated by 2% noble gases. The reaction has a total of a 15% yield, and we need to calculate how much ammonia is produced. Notably, the chemist does this particular reaction in two stages. They perform the reaction until the equilibrium point is reached, remove the ammonia product, and then add any extra feedstock to the space that's remaining in the vessel and perform the reaction again. So in this question, we've got to think about two different stages of processing. The chemist in this case first applies her feedstock to the reaction vessel and is going to get an output of ammonia at the end. She then is going to add more feedstock to the vessel and produce more ammonia. So we have to think about those two cases. And it's also really important to remember that our feedstock is composed of both the reactants for this particular reaction, which is the hydrogen gas and the nitrogen gas, as well as some contaminants. In this case, those contaminants are noble gases. And we've been told that it's a 2% contamination rate by the noble gases. So this is the first thing that we're going to have to apply to work out what volume of our feedstock is actually the reactants that we're going to be using. So here we can see that what we've done is we've applied the 98% to the 700 litres of the feedstock to find the actual volume of hydrogen and nitrogen that we've put into the reaction vessel. And we can see that we've got 14 litres left of the original 700 litres, that was the noble gases. These gases do not partake in the reaction, so we have to eliminate them early. Now we've got to think about this term yield. Yield refers to the percentage of the reactants by mole which are converted to products. So in this case, because we're using gases, we can use Avogadro's law, which says that equal volumes of gases are occupied by equal numbers of moles. So this means we can actually apply the 15% directly to the amount of gas that is being reacted. So in this case, because all of the reactant gases are in the correct stoichiometric ratio, it follows that if there's a 15% yield, 15% of the reactant gases are going to be converted to the product, in this case ammonia. So when we apply the 15% to 686 litres, we get this amount 102.9 litres. This refers to the amount of the reactant gas which is actually going to be converted over into ammonia. Once we've found that number, we can find out how much ammonia was produced in that stage one of the reaction. Now we know that the ratio of reactants to products is 4 to 2, so 2 to 1. That means that the volume of ammonia that is produced is going to be half of the volume of reactants that we put in to make that ammonia. So in this case, this will come out to 51.45 litres of ammonia. We're going to keep this number for later because we need to work out the total amount of ammonia that has been produced. Now we have to think about stage 2. So let's just consider what's happened in the reaction vessel at this time. 102.9 litres of reactants have been converted to products. We have lost 102.9 litres of gas in the vessel. The ammonia has been liquefied and taken out. That means we add 102.9 litres more of feedstock. And the key to this question is that, again, 2% of that feedstock is going to be the noble gas contaminant. And we can work out that 2.058 litres of that new feedstock is going to be that contaminant, which means that the actual volume of reactants that we've got at this time is 683.943 litres of reactants. That's what's going to participate in stage 2 of the reaction. But again, we have to apply our 15% yield. So we apply the 15% and we find that 102.59145 litres of the reactants will actually participate in the reaction. This is what we expect because now that more noble gases have accumulated in the reaction vessel, we would expect that a slightly smaller amount of the reactants will be participating in the reaction than they were in stage 1. And then we can just apply the same mathematics that we did previously, halving this figure to find the actual amount of ammonia that we produce in stage 2. So now we have the 2 volumes of ammonia that we've produced in stage 2. So now that we know both the amount of ammonia produced in stage 1 and stage 2 of the reaction, we can sum this to find the final volume of ammonia produced. And that's about 102.7 litres of ammonia. Notice that I've put all the different decimal places, as many as my calculator output provides, into all intermediate stages of working. This is to prevent any introduction of error by excessive rounding in intermediate stages. Also remember to put your units in at every intermediate step. I then find the number of moles of ammonia that was produced by dividing by the molar volume, which is 24.79, and then we get the final number of moles, which is just over 4.1 moles of ammonia produced. We can convert that to a mass by multiplying the number of moles by the molar mass of ammonia in this case. And at the end, we get a mass of 70.6 grams to 3 significant figures as required by this question. Thanks for watching. See the link to the previous video here, the next video here, and go down to below for the links to the website. My name is Ross. Thanks very much for watching. Hope to see you next time.